next paper is paper number 71H. The title of the paper is Multi-Component Kinetics and Mass Transfer Influences in Heterogeneous Photocatalysis. The authors are Craig S. Turchee and David F. Hollis. The work has been performed at North Carolina State University. Our speaker is Craig Turchee. He is currently a PhD candidate at North Carolina State. He received his BS degree at Texas A&M University. Mr. Turchee.
If I could have the first slide, please. The title for our talk, as you can see here, is Multi-Component Kinetics and Mass Transfer Influences in Heterogeneous Photocatalysis. This is quite a general title. I'd like to start off by saying that what I'll be discussing this morning is the degradation kinetics of the binary system with the two reactants benzene and perfluoroethylene. I realize many of you may not be familiar with heterogeneous photocatalysis, so I think a brief overview is in order. The process is a technique to degrade low levels of organics or fluoroorganic contaminants in aqueous systems. The first step in the process is the absorption of ultraviolet photons by the catalyst. The catalyst we use is a semiconductor, and as such has a band gap, represented here by Eg, between the highest filled energy level in the catalyst and the next vacant energy level. The absorption of ultraviolet photons occurs to photoexcite electrons in the valence band, or that's EV. The photoexcited electrons enter the conduction band where they have a greater mobility and become a highly reactive species. They leave behind in the valence band an electron vacancy known as a hole, and this is also a reactive intermediate. These two species then form a redox pair, which is what drives the reaction. The requirements for the photocatalytic reaction are fourfold. We need ultraviolet illumination to photoexcite the catalyst. The illumination must be of sufficient wavelength to excite the catalyst. That is, the entering photons must have an energy to exceed that band gap that I showed previously. For the catalyst we use, this represents 380 nanometers, or something in the near UV. Water is also necessary in the reaction. It is oxidized at the surface and provides the oxidation species. The semiconductor catalyst, of course, is necessary. We use titanium dioxide for a number of reasons. It's been found to be the most photocatalytically active of the semiconductors that have been examined. It also does not photodegrade like many semiconductors do. And in addition, it's relatively inexpensive and prevalent in the pigment industry. Lastly, molecular oxygen is necessary to provide the other half reaction of the redox couple. It is reduced by the conduction band electrons at the surface of the catalyst. The lower half of the slide shows a representation of the mechanism that occurs on the catalyst particles in solution. Ultraviolet photons are absorbed within the catalyst. They produce the electron-hole pairs. Holes can migrate to the surface and react with either hydroxyl groups or water molecules, which are prevalent on the surface of the catalyst, to oxidize these groups to hydroxyl radicals, which a lot of evidence has suggested are the primary reacting intermediates. They attack the organics and provide the oxidation. The other half reaction is the reduction of oxygen, also at the surface of the catalyst, to form the superoxide ion radical, which then can proceed through a number of different chemical pathways to eventually produce more hydroxyl radical, most likely through a peroxide intermediate. The motivation for this research, and this is out of focus. The catalytic system has been used to successfully degrade a number of single component systems. The earliest work was done with chlorinated and brominated methanes and other short chain halocarbons. More recently, some of the more toxic compounds, such as chlorinated benzenes and phenols, and even some of the highly toxic compounds representing substituted aromatics, typically like dioxin type compounds, have been successfully degraded. In most of these systems, the degradation kinetics were not investigated very thoroughly. In a lot of cases, the initial rate studies were performed, and that set the basis for our research. In 1983, the U.S. Department of Interior, in cooperation with a company in Texas, published a report where they degraded a 5-component system. This was the most complicated system that we've seen to date in the photocatalytic degradation. So we endeavored to model this system. However, due to a number of inconsistencies in the data, we think primarily due to the complexity of working with a 5-component system, the modeling results were inconsistent. We then decided to investigate our own more complicated system, that of a binary system, under more highly controlled conditions in order to meet the following objectives. We wanted to use pure component studies, or single component studies, to obtain kinetic parameters, and then apply them to the binary system to see if they would adequately predict the degradation. We'd also be following the evolution of product. The final evolution to the oxidation reaction is CO2, and in the case of chlorine-bearing compounds, HCl is also formed. Secondly, we wanted to estimate the effects of intermediates, or indeed see if any intermediates were important. The reactor we used for the photocatalytic studies is one we've used in our lab for a number of years. It's a recirculated batch system. The quartz annular reactor for the photocatalytic system is shown here. It contains one fluorescent UV light down the center line and has 6 other fluorescent bulbs surrounding the reactor. The solution is recirculated through a probe reservoir, which contains a CO2 gas sensing electrode and also a vapor headspace. The vapor headspace provides the oxygen that's necessary for the reaction. And to enhance mass transfer from the oxygen headspace into the liquid phase, we mounted a stir bar vertically at the interface to agitate that. Sampling was done through the liquid phase from a sample port, and a GC was used to analyze the reactant concentrations. Finally, the entire system was circulated to a cooling bath to provide cooling and keep the temperature at 20 degrees C. The initial runs, as I mentioned, were the single component runs, and this is an example of a single component degradation of perchloroethylene, PCE. The squares are the decrease in PCE concentration that proceeds to 0 in roughly 20-30 minutes. And you see the almost instantaneous evolution of CO2 as measured by the gas sensing electrode. On the other hand, when we look at benzene, we again see the rapid decrease in benzene concentration. However, now there's a serious lag time in the evolution of CO2. This was not totally unexpected, since benzene is a much larger, more complicated molecule than perchloroethylene. What we thought was happening here was the formation of hydroxylated aromatics, such as hydroquinones or cresols, which have been seen in the degradation of phenols. These would then proceed through ring opening and eventual decarboxylation to form the CO2. For PCE, on the other hand, we'd expect a more straightforward degradation, possibly through a phosgene-like intermediate, which would rapidly hydrolyze. The model we were using for the binary system is a Langmuir-Henshelwood or Howring-Watson rate law. We've made the modification now that the degradation is based in terms of the total amount of reactant in the system, because we have a headspace in the reactor, and these volatile organics will partition between the vapor and liquid phases. The correlation between those two phases was through Henry's law, which is entirely valid at the low concentrations we're working at. We assume then that the vapor and liquid were in constant equilibrium throughout the reaction. Again, the decrease was in terms of total reactant in the system, whereas the reaction itself occurred in the liquid phase. These K and K values in both of these equations were determined from initial rate studies and are the parameters that we're estimating with these single component runs. Well, as most of you know, the plot to determine the validity of the Langmuir-Henshelwood rate law is reciprocal rate versus reciprocal concentration. Here we see the summation of all the single component runs, and the lines which we use to determine the kinetic parameters we'd be using to predict the degradation rate. When we took this model and applied it to the binary degradation data, we obtained the following results. We see that the model predicts a much more rapid decrease in concentration than was observed experimentally. We took this along with the lag time we saw in the benzene degradation to mean that there were important benzene intermediates which were effectively competing with the primary reactants for the reactive species. In order to correct for this, we incorporated an intermediate term in our model based on the following simplified stoichiometry. Again, PCE was assumed to degrade rapidly to the 2 CO2 molecules corresponding to the 2 carbons in perchloroethylene. as well as the HCl. Benzene, on the other hand, was assumed to go through some intermediate species, which is more likely a series of intermediates, before it eventually formed these 6 CO2 molecules. We assumed in this derivation that the total amount of intermediate and benzene in the reactor never exceeded the initial benzene loading. That is, the degradation was a stepwise or series fashion. The model then looked in this fashion. We now have 3 differential equations which we solved. The amount of CO2 evolved, which is also predicted, was done on the basis of stoichiometry. As a reminder, these parameters for benzene and PCE were obtained from the initial rate studies of the single component systems. The Ki for the intermediate were obtained as a best fit to the binary runs which we carried out. We're looking not only for a good fit of the degradation data, but also the CO2 evolution, which we also followed. This set of data, you might recall, is the same set I showed you just a moment ago, only now we've incorporated the intermediate to our model, and we see we have a much better correlation between the predicted degradation rates and the observed experimental rates. The CO2 evolution curve is shown here. The model prediction is the smooth curve. The data points are the x's, and the dotted line represents the theoretical concentration of intermediate, which we as yet have not looked for intermediates, but this is just what the model predicts. We see we have quite a good correlation, except down in this very low time region. There are a couple of reasons that could cause that. One, there's a slight probe lag, well, a significant probe lag actually in the low time region. However, that factor is probably not too great. It's more likely that since benzene is proceeding through a number of intermediates rather than just one, we're not weighting the initial time region properly. Another set of data here showing the CO2 and stacked on top of the degradation rate. We see again we have a good correlation between the experimental and predicted degradation. In conclusion then, we can make several conclusions from the experiment. First of all, we witnessed total degradation in both the pure component and the binary degradation system as based on a carbon balance with our CO2 probe. There were no significant PC intermediates implied or seen in any case. Benzene, on the other hand, was seen to produce important intermediates, and they effectively competed with benzene and PCE for the reactive species. The initial rate model was not able to predict degradation rates when intermediates were present. The only time that the initial rate model predicted temporal data well was when no intermediates were around. The only data we had for that was the single component PCE runs. And in these cases, we did get good correlation between the model predictions and the experimental data. When we included a logically consistent term for an intermediate in our model, we were able to get quite good correlations between the degradation data and the model predictions. In future work, we're endeavoring to identify and measure the concentrations of the intermediates which we believe to be in the benzene system. We've also got some data from previous work where one intermediate was observed and the concentration of that intermediate was measured, and we'd like to apply our model to that system and see how well it fits the data. Thank you, and I'd like to address any questions now.
You showed us the fit for the single component systems to get the PCE and benzene parameters, the two parameter model. Then went on, and I didn't quite follow your explanation. When you added the inhibitor component,
yes,
the third parameter, did you go back to the benzene pure component results and adjust the benzene absorption parameter to allow for having added the inhibitor component as well, inhibitor parameter?
We've not done that as yet. The data, you might have noticed, was quite recent, and that's one thing we'd like to go back and do, try and predict the benzene pure component data with the model. The parameters were obtained from initial rate data, so the effect of the intermediate on those parameters should not be important.
But you showed the fit for the integrated result?
Yes.
Okay.
A number of your chemical species should absorb in the UV. If you allow
of
caused
the,
some shift in your behavior.
yes, most of the aromatic species absorb further into the UV than what we're employing. The lamps we employ emit nothing below 300 nanometers, and their primary emission is around 360 nanometers. Most organics absorb somewhat lower than that in the UV.
Any other questions? Thank you very much, Karen.